In this series of videos, we're going to look at how water uses its polarity and intermolecular attractions to dissolve a variety of solutes, starting with simple ionic solutes such as NaCl. We know from the general formula of dissociation reactions that water pulls apart the negative and positive ions as soon as that substance is added to water. But what exactly does water do? If we take a look at the structure and polarity of water, we can see how it interacts with the ions in an ionic solute. We know because water has an asymmetrical distribution of lone pairs, oxygen has 2 pairs of electrons and hydrogen has none, that oxygen has more negative charge than hydrogen does. Additionally, because oxygen has a much higher electronegativity than hydrogen, it is going to pull the electrons in each bond towards it, giving it an even stronger partial negative charge, which in turn can attract to the positively charged ion in our solute, in this case, sodium. Assuming we have enough water, that means that more than a single water molecule is going to attract with the positive ion. These are what we call ion-dipole attractions, as we saw in the previous video series. Conversely, because hydrogen has a partial positive charge as a result of water's polarity, the hydrogens are going to form ion-dipole attractions with the negatively charged chlorine ion like this. Now, if we consider a thought experiment, let's say that we had 2 beakers, one that contains salt and one that contains water. Let's say that we have this much NaCl and only this much water. Is it possible to dissolve this mass of NaCl with this volume of water? The obvious answer to that is no, simply because we don't have enough water. Now, the reason why we need enough water, so to speak, is by looking at the bonds and by looking at the ion-dipole forces, we can see why this requirement is there. NaCl, as an ionic compound, has a full positive charge and a full negative charge, whereas because water is only a polar covalent compound, its charges are only partial negative and positive charges. That means because chlorine has a much stronger negative charge than the oxygen does, sodium is naturally going to attract to the stronger negative charge. So how is water going to cause these to dissolve if water's charges are less strong? Well, this is an example of quantity over quality. Even though one positive pole on a hydrogen is not strong enough to pull the chlorine away from the sodium, we don't only have one water molecule. If we have enough water molecules, and if those water molecules are moving in the opposite direction as the water molecules that are attracted to the sodium, the movement of water molecules can cause the 2 ions to pull apart into something that we see here. Now, we can then ask the question, if these charges are stronger, and if they want to attract to each other, if a positive charge wants to attract to the strongest negative charge, and vice versa, how do the 2 ions stay separate? Well, the answer, as we've seen here, is because of water once again. Assuming that we have enough water, the sodium ion can be surrounded by the oxygen side of many water molecules that form a shell around the ion and stop it from being able to return to the chlorine ion here. Likewise, chlorine is surrounded by a shell of water molecules that use the positively charged hydrogens on them in order to effectively blockade the chlorine ion and stop it from being able to get back to sodium. When these structures have formed, when each of the 2 ions are surrounded by water molecules, this is the point in a solution where our solute is no longer visible because the ions cannot return to each other because of water. These structures formed with water surrounding each of the ions are what we call hydration shells, which literally means shells of water that stop the ions from getting back together. In the next videos, we'll look at a different group of compounds that also dissolve in water but do not undergo dissociation reactions like the one that we see here.